So welcome to this video series about the simulation-based assignment, short SBA. My name is Annette Ehlert and I'm a technical product manager at PTV, and I would like to take you through these videos that contain a lot of information about and around SBA. These videos represent the status as of PTV Visum 2023 and are directed towards modelers who work on transport and operational models using Visum. The video series consists of several videos that can be watched in sequence, but you can of course also watch single episodes based on your existing knowledge or on current project applications. So the first video is an introduction, followed by demonstrations in the software. So the structure of the videos is presented on this slide. After the introduction, we start the demos in the software with a network coding, then profiling of demand, setting up the assignment, and this is followed by two videos that demonstrate what results are obtained and how they can be analyzed and visualized. So after that, we focus on demand calibration using dynamic matrix estimation. And finally, we will look at the process of generating subnetworks and their export to PTV Visum. And the series will end with some tips and tricks. So as mentioned, the first video is an introduction. So we will start with an overview of private transport assignments in Visum, and then move to dynamic assignments, and then specifically to the simulation-based assignment and its basic principles. So this slide shows an overview of all private transport assignments in Visum. So they can be differentiated into static assignments and dynamic assignments. Dynamic assignments add the dimension of time, whereas in static assignments, it is assumed that all trips start and finish within the assignment period. This is a simplification that in some applications are useful and also appropriate. So let's have a closer look to static assignments. The majority of you will be familiar with static equilibrium assignments, in which Wardrop's first principle is applied. So the most used methods are the classical equilibrium assignment, B conjugate Frank-Wolfe, and also Luce. Additionally, there are some special methods, assignment with ICA and the tribute method. Assignment with ICA is sometimes called quasi-dynamic. We will come back to that in a minute. And the tribute method is associated with the use of tolls and some specific assumption about the distributions across the driver population. So furthermore, we have stochastic equilibrium methods and the incremental assignment as the only non-equilibrium assignment. So for dynamic assignments, we distinguish between methods that use analytical relationships and the simulation-based assignment that makes use of a simplified simulation. So now let's have a look, how does the simulation-based assignment fit in. We take also dynamic assignments in Visum for that overview into account. So let's start at the top. Assignment with ICA. It is sometimes also called quasi-dynamic because of the ability to also calculate Qs. Here, impedances at junctions consider the details like the geometry of junctions, signal timings, and generally control of the junctions. So moving From these static assignment to dynamic assignments, it adds the dimension of time. And therefore, this also adds complexity. More data are needed, and also the calibration efforts are higher. In Visum, we have different dynamic assignments. Duo and the stochastic dynamic assignment are analytical methods. So that means they are based on macroscopic relationships between traffic flow and density. Then the simulation-based assignment, as the name suggests, simulation is used here. That adds precision. So for example, signal timings are directly considered. And as a consequence of that, platoons and also green waves can be modeled more realistically. So looking across products, namely Visum and Visum, mesoscopic assignment methods are available in both. So what are the differences? So in Visum, the mesoscopic simulation is used within the simulation-based assignment. So it works for larger networks than in Visum, and also big models in Visum are faster to develop and have shorter run times. Visum, in contrast, is more expressive, so it's more detailed in terms of characteristics of drivers and contains also the possibility to include vehicle-actuated signals. So we have in both products a hybrid option. In Visum, that is a hybrid macro-meso simulation as part of SBA. And in Visum, it is a hybrid meso-micro simulation. So again, that can add detail to the results. So why do we use dynamic traffic assignment? Static methods have simplification. And as I said, this is maybe acceptable in some cases. Here the dimension of time is neglected, so we assume all trips start and finish within the assignment period. So therefore, a static model is not able to show the hotspots of congestion at different times and in different places. However, that is something dynamic assignments can do. So DTA is useful for larger networks to represent the effect of long distance patterns more realistically. So therefore it's possible to see how congestion evolves from traffic moving into the city center in the morning. And you can do that, you cannot do that in a static model. So DTA has also greater precision for modeling the effects of congestion. So in a dynamic model, you can see when and where bottlenecks are recurring and how queues form and how congestion is resolved afterwards. The simulation-based DTA doesn't rely on simplified relationships between flow and delay, but considers the interaction between individual vehicles. And also the signal offsets are explicitly represented and affect the travel times in the network. So what are the use cases for DTA? So generally, DTA is useful in heavily congested networks to represent the formation and resolution of congestion, which affect route choice over time. So short and direct routes are generally attractive, but in peak hours, alternative routes are more and more utilized because of the additional lost time due to congestion. You can also model time-varying policies, so that applies generally to temporary changes that could be referring to speed, to tolls, but you can also model something like road and lane closures. Incident and roadwork management are applications, as well as evacuation plans. And as mentioned before, dynamic assignments are useful to get more realistic inputs for microsimulation and therefore are useful for multi-resolution modeling between different levels. So let's now focus on the simulation-based assignment. The basic principle of how the assignment works is similar to static assignments. So there are basically 3 steps. We have the shortest path search, the distribution of demand across the routes, and a network loading process. So the first 2 steps are done per time interval. So here we add the dimension of time, and the network loading takes the departure times of the vehicles into account. As mentioned, for the network loading, the simulation is used. So the key concept of the simulation-based assignments are that demand and supply can change over time. The vehicles departing at different times are assigned to different routes because the attractiveness of a route can change over time, and the equilibrium condition is extended also to time. So that means vehicles departing at the same time between the same OD pair but take different routes must have the same experienced travel time. So now let's have a look at the simulation. So the science behind the mesoscopic simulation is the same as in PTV Visum. We use a simplified curve following model. Then we have a lane selection model, and junctions are modeled by signals and by gap acceptance. And now we will have a look at each of these features in more detail. So a simplified model for car following is used, and here we distinguish between 2 states only. So either the vehicles travel at their desired speed, or the vehicle follows the vehicle in front with a temporal distance that is equal to the reaction time plus the time it takes to travel the standstill distance. So the simplification comes from the fact that acceleration and deceleration is here neglected. For lane selection, also a simplified lane selection model is used. So lane selection happens when a vehicle enters a link, and there are certain conditions on which a vehicle selects a link. So a vehicle has allocated a route, and from the next link, it must be ensured that it can follow its route. So also the next link on the route can be reached without the need to change lanes. And the other condition is that on the lane, the transport system of the vehicle is permitted, and also on the outgoing lane turn from that lane. So now we come to some basics of network coding. As in any transport model, the permitted transport systems for links, turns, and connectors must be defined. Then for links, it is necessary to define the number of lanes and the free flow speed. Because simulation is used here, the capacity is not an input for SBA. So then junction control must be modeled. There are basically 2 components of this, the signal times and gap acceptance. And the right-of-way is essentially determined by the control type. Then the junction geometry must be defined. So this concerns mainly the definition of pocket lanes and their lengths. Then there are certain parameters of the transport system that are related to the car-following model. So that is the SBA reaction time and the effective vehicle length. And then there is an additional parameter, the SBA maximum wait time. So that influences the behavior at junctions in case of conflicts. Then the temporal distribution of demand can be modeled. So this can either be done by a time series with percentages or a set of matrices with time information. The changes of the supply can be modeled. So in this example, that is a speed reduction over some short period of time. So and then the transport system of lanes and lane turns are considered. However, when you initially set up a transport model, lanes and lane turns inherit the transport system from the corresponding links and turns. So in the first step, you do not have to care about that because that is automatically ensured that there is consistency between lanes and links and lane turns and turns. Note that the simulation considers the transport system of lanes and lane turns. So if required by the use case, you can adjust transport systems for lanes and lane turns. For example, to model lane-based applications. So typical examples are HOV lanes, taxi lanes, bus lanes. So if required, you can reduce the transport system from the links on the lanes to model these use cases. So next we come to junction control. Junction control is modeled by signals and gap acceptance. And that relates also to lane turns and major movements. For both of these, Visum applies some defaults. Lane turns are automatically generated based on the number of incoming and outgoing lanes, and the major flow movement is derived based on the rank of link types. Signal timings must be coded, including the offsets, and you can model gaps, but also there are some standards applied that are derived from the highway capacity manual. So that means generally Visum will derive conflicts. So conflicts typically occur where these lane turns cross or if these lane turns have the same destination lane. And then gaps for the lower ranked movements are automatically derived. So I mentioned before that there is a hybrid macro-meso simulation available, and this is implemented as an additional option within the SBA procedure. So let's now assume that you have a regional model currently with static methods, and for the central part, there is a need to look at the congestion pattern over time. So in other words, it requires the use of SBA. So now you have three options. The first is you apply SBA in the entire model. So the advantages of that is that you have the most precise representation of congestion pattern and rerouting effects in the entire network. The additional coding you do for SBA results in an improved model so that you use Visum as a data hub to store additional data. And these additional data could be beneficial for other traffic engineering applications or multi-resolution modeling. And the results enable to cut subnetworks with a dynamic demand profile. Again, that is beneficial for multi-resolution modeling. On the other side, you can have disadvantages. That could be longer run times, the coding efforts you need to do, and also the calibration efforts are reasonably high. So the second option could be to cut a subnetwork and apply SBA only for the subnetwork. So that, of course, has the advantage that everything is faster. You do not need to code as much. The runtime is faster, but there is also a big disadvantage. Any improvements you do in the subnetwork is decoupled from the parent model and therefore lost for the parent model. And you have additionally an option. You work with the full model, but you apply the additional option within SBA, the hybrid macro-meso simulation. Again, also here there are certain advantages. You do not need to create the subnetwork. The runtime is faster than on the full model. Also, your coding efforts are smaller. And again, the improvements you do for the network are in the parent model. Also here you can cut subnetworks with a dynamic demand profile. The disadvantage is that you do always as much as you need for the current project. So how to decide? Typically, it depends on the objective of the project, but of course also on other requirements such as runtime requirements you may have, the efforts for calibration and for coding, and maybe also how often you might to reuse whatever you have coded in the full network. So, and finally, I would like to give you some insights how the hybrid macro-meso simulation works. So again, here we assume that you have a regional model and would like to study the effects of roadworks in some part of the city, plus maybe the introduction of HOV lanes on the nearby freeway. So these areas are here colored in a light green. So in these areas, we apply the mesoscopic simulation, whereas in the rest of the network, travel times are derived based on macroscopic principles. So that means using volume delay function with capacities and volumes. So both approaches lead to so-called travel time functions. So these are generated for each of the network objects, so for links and turns in the corresponding area. And on the x-axis, it shows the assignment period, and the y-axis, the travel time for the corresponding network object. So for the meso areas, they show varying travel times over time, so that is shown on the right side. So more precisely here, the experienced travel time on each point of time during the assignment period is known and changes over time. On the opposite, for the network objects in the macro part, these functions are constant over the assignment period. So with this, we are at the end of the introduction, and the next videos will be demonstrations in the software.